And so looking at the appendix D data, we're just going to go from H2O liquid to H2O gas. And so we look here. Some of these calculations we'll just do. Go ahead. So, for example, H2O liquid to H2O gas. H2O liquid to H2O gas, we're going from 1 mole to 1 mole. The restriction here is the H2O gas has to be at, H2O gas is going to be at what pressure? Actually, what is the pressure here? Let's find out what the pressure is. Is it 1 bar or is it 1 atmosphere? Because, it changes the boiling point. The boiling point of water is 100 degrees C at 1 atmosphere of external pressure. But if we're at 1 bar, even though it's close, it's just slightly different. But this data table is for 1 bar in 1 molar. It's all right. Let's go with that. You know what the boiling point of water is at 1 bar?
No.
Oh, wow. Actually, I don't either. I don't know. I should calculate it. It's one of those things. But anyway, this is 1 bar here, and then the temperature is at. We're going to do this under standard conditions. In standard conditions, this is 1 bar. We don't have no aqueous solution, so 1 molar is applicable, and 298 Kelvin. And so that means the H2O liquid is at 298 Kelvin, and the H2O gas is at 298 Kelvin, right? We don't change the kinetic energy. This is the potential energy that's changing. The potential energy is due to the hydrogen bonding holding the water molecules together in the liquid state. And so, anyway, with those restrictions, then we can do some calculations. We can do, let's do our delta G naught. This is going to be delta G naught at 290 Kelvin. Delta G naught is equal to delta H naught minus T delta S naught. And both of these are going to be 298. That's no problem. 298. And T will be 298 Kelvin. Okay, so delta H naught at 298, we can just calculate it. It's going to be the delta H of formation of the product, minus 241.8, minus the delta H of formation of the reactant. So it's going to be a minus 285, and it gives us 44.0 kilojoules. And so delta H is just 44.0 kilojoules. T is 298 Kelvin. Now let's go and figure out what delta S is. And so delta S is the absolute entropy of the product. The product is H2O gas, 188.8, minus the absolute entropy of the reactant. And since this is 1 mole and 1 mole, I'm just using these outright. If I had 2 moles, then I multiply by 2, or 3 moles multiplied by 3, or half a mole. Sometimes we'll have half because of formation reactions. Formation reactions, we often have fractions because we form only 1 mole. But anyway, let's go to this. It's going to be 188.8 minus 69.91. What is that?
119. Close to 119.
119. Okay, so 100 and what was it? 118 point. Let's get the number. We're going to carry all the digits because we want to compare. Actually, I have my calculator. So the entropy of the product is 188. The gas is water. 188.8 minus 69.91. Actually, this is a pretty decent backup calculator. These 99 cents. And so I get 118.89. But the units are different. This is going to be, the moles are going to cancel out because it's 1 mole, so moles cancel. This is going to be joules per Kelvin. So the kelvins cancel out, but this is kilojoules, that's joules, so we have to get them the same. And so you got to change either this one or this one. Let's go ahead and change this one here. For every kilojoule, there's 1,000 joules. So joules, now it looks good. And so let's go ahead and do that. 118.89 times 298 divided by 1,000. And so what we have is 44.0 kilojoules, and then this term is going to be minus 35.42. Actually, I'm only allowed one decimal. 42. Oh, actually, I'm allowed more because this is kilojoules. So 35.429 kilojoules. Now take a look. In this, here, delta S and delta H are going to impact. In this case, delta H is positive, whereas delta S is positive. Delta H being positive, this is not good for driving force, so it's bad for driving force, but this is good for driving force. And so which one wins? You know, delta H says no reaction, so there's 44 kilojoules that says no reaction. However, their delta S is 35.429, the delta S term. You know, the term has to be multiplied by the temperature because temperature is going to be a factor in that, dimensionally. So there's 35.42 kilojoules that says reaction, 44 kilojoules that says no reaction. Who wins? Well, the 44, because it's going to add up to plus 8.57. Plus 8.57 kilojoules. Plus 8.57 kilojoules means non-spontaneous. So we don't expect water to spontaneously boil at 298 Kelvin. Liquid water is the favor, non-spontaneous. Well, we don't, these delta G values, do we have a table, you know, how big do they run, how small do they run? You can see some delta G values over there on the table, minus 690, etc. Now, so in other words, we don't expect liquid water to spontaneously vaporize. You know, a little bit will. The bulk of it will remain liquid. There's another way of calculating this. The other way of calculating this is via this. You know, it should equal the sum of the delta G's of formation of the products minus the sum of the delta G's of formation of the reactants, right? And so let's go ahead and do that calculation here. If we look at it, the second column is in. So we take the delta G of formation of the product, which is this, minus 228.6. So I'll just enter that in, negative 228.6. Minus the delta G of formation of the reactant. So it's a minus 237.1, so it's plus 237.1. And this gives us 8.50 kilojoules. Well, we got 8.57 and we got 8.5. So the difference is this is 8.6, this is 8.5. There's a discrepancy here, right? Both of these should have given us the same answer, right? Should be equal. But there's some discrepancy, and in fact, that's what you're going to find. You're going to find a little bit of discrepancy between using the delta G's of formation versus the delta H and delta F. So which one's right, which one's wrong? You know, I don't know. I guess you could take the average, but we aren't even going to bother taking the average. You're just going to calculate one way or the other, whichever way you want. And you know, that's the answer you're going to get. And so if I calculate it this way, this is the answer I'd report. If I calculate it the other way, this is the answer I'd report here. And either one will be right. Is that okay? And so slight discrepancy because of the experimental, probably the experimental nature of the data and how the different data were derived. All right. So I wouldn't worry about this discrepancy so much. Now, what about if we change the temperature? You know, by changing the temperature, you change the driving force, right? Because delta G will change. And so by changing the temperature, you can make it more spontaneous or less spontaneous. And so the influence or impact of temperature, let's say impact of temperature. So in this case, let's take a look. If I increase the temperature, is that going to favor the entropy or the enthalpy? Increasing temperature favors the entropy. Is entropy driving the reaction or not driving the reaction? When I say good or bad, it's not necessarily. There's some reactions we don't want to happen. Right? I'm just saying good for driving force. And so the higher the temperature, the more biased the driving force is towards entropy. And so if we increase the temperature, we're going to favor entropy, favor the delta S term, and that's going to make it more spontaneous. Right now it's not spontaneous, but it'll be more spontaneous. You know, in other words, the gap here, you know, if I continue to increase the temperature, what's going to happen? Well, this term's going to grow. As this term grows, pretty soon the gap becomes smaller and smaller. In fact, I can grow this term big enough to cancel out this, because this is the bad term. If I want to cancel this out, then I got to make this term. If I can make this term 44 kilojoules, right? If I can make this term 44 kilojoules, then it's balanced. If I make this term bigger than 44 kilojoules, then we're going to have spontaneous driving force. And so decreasing temperature is going to favor the enthalpy. And if we favor the enthalpy, then it's going to be less spontaneous. And so here, yeah, if I make this term smaller and smaller, then the gap grows bigger and bigger, and this becomes less and less favorable, you know, more positive. We don't want that. And so what we can do is we can manipulate the driving force by changing the temperature. And so what we're going to do is we're going to just do a calculation, you know. This calculation would be, at what temperature will this reaction, or it's not a reaction, but at what temperature will this process transition from being non-spontaneous to spontaneous? And so the question here is, at what temperature will the process transition from non-spontaneous to spontaneous? Okay, there are different ways we can think of it. One way we can think of it is we want to make these two terms equal. Another way we can think of it is we want delta G not to be plus. We want, at the transition, it's going to transition from plus, you know, it's going to go from plus through 0 to negative. This is what we want for delta G, to go from plus to 0 to negative. So what we're going to do is we're going to set delta G equal to 0. If we set delta G equal to 0, this is going to equal delta H. This is delta H naught minus T delta S naught. All right, and then, okay, we solve this. In other words, we got to have delta H naught be equal in magnitude to T delta S naught, and then they can cancel each other out. The entropy term can cancel out the enthalpy term. And then we solve for temperature. The temperature is going to equal delta H naught divided by delta S naught. Now, the tricky thing is this temperature has to be, well, we need the delta H naught at 298, not at 298. We need the delta H naught at this temperature. Well, how can we get the delta H naught at that temperature? We don't even know what the temperature is. Right? But what we're going to do is we're going to make the assumption. You know, we assume what we said before, and then we're going to go ahead and just use the 298 Kelvin value here. Is that right? Well, no, not really, but is it going to be hugely wrong? No, it's going to lead to a small error, but Now, delta H naught was 44.0 kilojoules for this reaction. We're just dealing with a mole of water, so we don't have to put the moles. And then delta S naught is 118.89 joules per Kelvin. And then we got to convert it into kilojoules. So 1 kilojoule per 1,000 joules. And so what temperature will this spontaneously vaporize? And so let's take a look here. It's going to be 44 divided by 118.89 times 1,000. 370. 370.08. Okay, this is Kelvin, and so minus 273 gives us 97.08 degrees C. Well, I know the boiling point of water. Water should spontaneously vaporize at 100 degrees C, right?
At 1 ATM.
At 1 ATM. But I don't know the boiling point at 1 bar. I'd have to see. Is 1 bar bigger than 1 ATM or smaller than 1 ATM? Let's just take a look. They're close, right? But let's take a quick peek here.
About 1.01325 volt. 1 ATM is like about 1.01325 bar.
1 ATM is 1.01. So 1 bar is slightly less than 1 ATM, 0.9 something ATM. If it's a 0.9 something ATM, then it should boil at a lower temperature than 100 degrees C. And so even though this is off, because we know, water will spontaneously vaporize at 100 degrees C, we got 97, but it's not, it's a little closer than, because water at 1 bar boils slightly lower than 100 degrees C, so error is not. But, we expect a little bit of error because of this. And so, I already knew the answer. I already knew at what temperature this is going to go from non-spontaneous to spontaneous. That's going to be at the boiling point. Right? So, this is a calculation we can do. Now, is it possible to boil water at room temperature?
Yes.
Yes, it is possible to boil. Have you ever seen water boil at room temperature? How is that done? Let's see. By changing the pressure. Our vacuum is not strong enough. I've tried it before, and so let's just take a look quickly here at water. Physics has a strong enough vacuum pump boiling at room temp. So let's see this. Oh, well. Hope there's no commercial. This is an interesting vacuum pump. So there's some water, room temperature, and then this is a mechanical pump that, let's see. And there it is. It's starting to boil at room temperature. All right. Well, we can use thermodynamics to predict what pressure, that crank. Let's see, what pressure is that right now? Hard to read. That is in PSI, it looks like. And that would be a gauge pressure. Do you guys know the difference between gauge pressure and absolute pressure?
Yes.
Gauge pressure is arbitrary, zero. Zero gauge pressure is normal atmospheric pressure. So
With gauge pressure, we can have negative pressures. You know, negative pressures are very unusual because it doesn't make sense because pressure is generated by collision. So how can you have a negative collision? Well, you don't have a negative collision. It's just measured relative to some arbitrary zero, which we call normal atmospheric pressure. But anyway, how much vacuum do we need? We're going to do it in terms of absolute pressure rather than gauge pressure that we saw there. And so, can we use any of these equations? No, we can't use any of these equations because the pressure is fixed, right? All these equations have the pressure fixed. Now what we want to do is we want to alter the pressure. So can we alter the pressure or the concentrations? Yes, we can. But that means we're going to be under non-standard conditions. And so let's take a look at non-standard conditions here. And so far we have one way of altering the driving force, manipulating it, and that is change the temperature. It's easy, change the temperature. But keep the conditions under standard conditions. What we're going to do now is we don't want to go standard condition. What if we want to do it at a different pressure? Or what if we want to do it under a different concentration? How will that impact the driving force? Or what if we want to do it under different pressure, concentration, and temperature? You know, how are we going to deal with that? And the way we deal with that is this. This is from thermo relationships. From these thermal relationships, we're going to skip the derivation of this. You can look at the derivation in the book. But basically, we're just going to go straight to the equation. Delta G under non-standard conditions at some temperature T is equal to delta G under standard conditions at some temperature T. And so what we're going to do is we're going to just take our normal delta G under standard conditions and then correct it for non-standard conditions. And so the correction for non-standard conditions is going to go like this. It's going to go R, L, N, R, T, L, N, Q. It's going to look something like this. What this does is it just corrects this. And this is where Q is the reaction quotient. It's the thermodynamic reaction quotient. The thermodynamic reaction quotient looks like this. It's going to be the activity of the products divided by the activity of the reactants. And so let's take a look at this here. And so
Is that, can that be substituted with concentration? Is that lower?
yeah, the activities you call for aqueous solutions. The activity of aqueous solutions is just, we're going to assume it's pretty much this ideal concentration, the stoichiometric concentration. The activity of gases is just the partial pressure of those gases. Activity of solids and liquids are just one. And so the example here is we have this H2O liquid goes to H2O gas. And what we're going to do is we're going to fix the temperature at 298. And so we'll use 298 Kelvin room temperature. If the temperature is at 298 Kelvin, then for non-standard conditions, our delta G is going to look like this. It's going to be delta G at 298 under non-standard conditions is equal to delta G at 298 Kelvin under standard conditions plus R. R is just our thermodynamic gas constant, which is 8.3145 joules per mole Kelvin. times T, well, T is 298 Kelvin. Ln of Q. Our Q is going to be the activity of H2O gas divided by the activity of H2O liquid. Activity of H2O gas is just the partial pressure of H2O gas, and the activity of H2O liquid is 1. And so the equation that we're going to end up with is here is delta G at 298 Kelvin is equal to delta G naught at 298 Kelvin plus RT Ln of the pressure H2O gas. And so basically this is what we have to do. We have to find the pressure. You know, as the pressure increases, does it become more spontaneous or less spontaneous? So as Q increases, this term grows bigger and it becomes less spontaneous. As Q decreases, in fact, we want Q to be less than 1. If Q is less than 1, then this is going to convert this to negative. And that would make it more spontaneous, because more negative it is, more spontaneous it is. And so what we're going to do is this. We know what delta G naught is. Now, we can either use the delta G naught from the delta G's of formation or from delta H, delta S. Which one do you want to use? The 8.58 or the 8.50? 8.50? It doesn't matter. We'll just use one. But, you know, the other one will give you a slightly different answer. And so we're going to go ahead and use the 8.50, you said? 8.50 kilojoules. And so what we need to do is, in order to make this spontaneous, we have to cancel that out. This is positive. This is not good, right? And so what we need is, we need this term to equal negative 8.5. So if we have plus 8.5 minus 8.5, then good, boom. That'll bring it to equilibrium, which means we just bump it, this term more negative, bump it down a little bit, and then we go spontaneous. And so we want this to be negative 8.5 to cancel. And so how do we do that? Well, basically this is it. We just say that what we want to do is we want these two to add up to 0. So we want this. We want delta G under non-standard conditions at 298 Kelvin to equal 0. If it equals 0, then it's going to transition from positive to 0 to negative, right? We want to go from positive to 0 to negative. And so we need to know where the transition point is. And so this is why this is 0 here. And this is going to equal delta G under standard conditions at 298 Kelvin plus RT Ln Q. I'm just going to leave it like this for right now, where Q is the pressure. And then I'm just going to solve this. This is going to be delta G naught at 298 Kelvin is going to equal minus RT Ln of Q. And then what we're going to do is we're going to solve for the pressure here. And so let's get this. Ln of Q, which is the pressure, is equal to delta G naught over RT to the negative. Now, Ln of Q is the pressure again, so we'll just say Ln of P is equal to minus delta G naught over RT. Now we're going to raise both sides to E, or whatever. We'll just get rid of the natural log, so that the pressure is equal to E to the minus delta G naught over RT. Now the delta G naught we have to keep track of, because this is the delta G naught at 298 Kelvin. It's good, and that's the temperature we're interested in. So this is delta G naught at 290 Kelvin here. And so we said we're going to use the 8.5. So this is going to be minus 8.50 kilojoules. And then R is 8.3145 joules per Kelvin. This is 1 mole, so I'm going to get rid of the mole since we're dealing with 1 mole. And then T is 290 Kelvin. Now there's a mismatch in units, you know. And so let's convert the joules to kilojoules or vice versa. Actually, you know, this one, I'm going to just convert the the kilojoules to joules on the top.
All right, so let's see what we got here for the pressure. And so this is going to be 8.5 times 1,000. Oops, turn this on. 8.5 times 1,000 divided by 8.3145 divided by 298. All right, and then it should be negative, so I forgot to put them there. And then e to raise to this power. So do, oops, wrong. I just cleared it. All right, let me do that again, unless somebody already has it. Shift keys and then located in a different spot like this. 8.3145 divided by 298. With that, and then I gotta go shift E answer.
0.032. Let me see the big 0.0323 units bar. 0.0323 bar. This is what we call 32 millibar. 32 millibar is, a millibar is close to, not really close, but somewhat close to a millimeter of mercury or torr. And so this is about, 30 something millimeters of mercury. Normal atmospheric pressure is 760 millimeters of mercury, right? So this is it. And so if we drop it, so that vacuum pump must have been capable of reaching a pressure of this, because if we drop the pressure down to here, then it's at equilibrium. So, and then if we drop the pressure a little lower, it's really going to start to boil. Does that make sense? Yeah? And so at what pressure will water boil at room temperature? At 32 millibar. A vacuum. Now, our vacuum is quite weak. This is nowhere near, the. This is maybe half an atmosphere. Probably isn't even half an atmosphere. Maybe 3/4 of an atmosphere. This is a really weak vacuum. So, will water boil at this? This would be more like 500 millibar. Will water boil there? No, it won't. So let's go, about half an atmosphere. What we're going to do is we're going to do this now. And I want you to do this. This will be a challenge question. Let's go with 500 millibar. For water to boil at 500 millibar, what must the temperature be? For water to boil at 500 millibar, what must the temperature be? I think we have the